I don't really. No, yeah, I don't.
So one of the things you did in that section that I just gave back to you is you verified that something was a solution to a differential equation, which means somebody somewhere solved it. But I'd rather see if I can find some qualitative things out, some information, even before I solve. Can I get something about the solution before I've done any math? And then I might ask myself a bunch of different questions, like, what's happening near a particular point? What's happening as we go off to positive infinity? What happens if I could roll the clock back and go to minus infinity? What information can I get without ever actually solving my differential equation? This is most commonly done with first order differential equations as opposed to higher order. So let's assume that we have a first order differential equation. And it doesn't matter what I'm using for my independent variable. One piece of software I'm going to use today is going to use X, the other one's going to use T. So I'll flip back and forth between the two, but it doesn't really matter. We just swap out the letters. The basic idea is that that function f of xy tells me about my slope. Because that's what this represents. That's change in y. That's slope. So we'll call this a slope function or a rate function. So if I pick a particular point, I could actually use that function to tell me the slope at that point. Here's an example. Y prime is 0.02xy. If I give you a point, say the point 2,3, you can tell me the slope of whatever solution I would get at the point 2,3. What is y prime at P? Please notice I'm not plugging in just the number. I'm using an evaluation bar. Like we did dy dx evaluated at a point. I'm using that vertical bar to mean plug in both parts of P. It's got to put in x and y. So if I were to create an image without actually solving squat, at this point, P, I know whatever graph is the solution has a slope of 1.2. So I can draw a little bitty piece of a line. The textbook calls it a lineal element, a little bitty piece of a line. And I can put it at that spot. Piece of cake, right? I did 1 point. Let's do 1,000. I'm not doing this squat by hand. Not going to happen. So, several different options in front of us. I could go to my computer and open the grapher. This is the software we use to graph stuff. Native to the MacBook, I've chosen the two-dimensional graph. By the way, on our Canvas page, there is a short video on how to do this. You don't have to do it from scratch every time, but I want to put in the derivative being our equation, right? So let me think about the slope of that little straight line piece. That's change in x, change in y, right? That's not y equals. So I'm going to go back here and I'm going to get rid of that y equals part. And I want to write change in x and change in y. Calc 1 question. What symbol did we use for change in x? A little upside. That's a letter. Capital Greek. It's a capital delta at that. I'm going to type the word delta using a capital D. D-E-L-T. Watch what happens as soon as I push the letter A. Turn into a triangle. It knows that's what I mean when I write delta. But I want it to be of x and y. That means I need a vector with an x and a y in it. Over to the right, top corner, there's a little sigma right here. If I click on that, it opens up a bunch of stuff, and one of those is a vector. Second row, third one from the right is a vector. So I can tell it what I want change in x and change in y to be. Our equation, y prime equals 0.2xy. That's change in y over change in x. So if I want to use that for the change in y, what do I use for change in x? That sounds a little absurd. We decided the slope at our specific spot was 1.2. If I were to write that as a fraction, 1.2 over what? 1. So I'm going to tell it I want to make the change in x to be 1, and then where I put change in y, I can put our equation. So I'm going to set this equal to another vector. And that vector has as the x part, it's got 1, and as the y part, it's got 0.2 times x times y. And then my calculator, my computer, will draw all this stuff for me. Look, a whole bunch of arrows. Now it uses a rainbow of colors here. I hate that. So I'm going to tell it by clicking this inspector up here, I'm going to tell it just use one color. See, it's got this checked thing, says use colors, turn that off. Then I can see what's going on. Now we picked the 0.23, right? So notice if I grab this, change your action from the little arrow to a hand, you can grab the picture and move it. There's the 0.23 right there. If I were to draw an arrow whose tail was at that dot, it should be going a slope of 1.2. This is called a direction field or a slope field. And I can do this as long as I have an equation, dy dx equals stuff. Now I will also tell you that you don't have to use the grapher. Let me turn this off. Where is my stop share? Right here. On our Canvas page. Like I said, there's the video for how to draw slope fields in grapher. It's in the handouts and examples section. By the way, up above that, reference files, there's that thing about Malthus, the exponential growth in food. Way down here is a web link to an app called Slopes. It's available for iOS or Android. I don't care. You can put it on the Mac. It doesn't run natively on a PC, but it will run on a phone or an iPad if you've got one. And Slopes looks like this. Let me share that so we can see it in the Zoom link. Now, there are a lot of things it does here. The thing I want to look at are slope fields, which is what we were just doing. And it gives me an equation, y prime equals. So I could go up here and I could tell it what I wanted. Now I wanted to do 0.2 times x. Oh, wait a minute. Notice down here, unfortunately, this assumes my independent variable is t, not x. T, y. That's going to give me the same picture. It's kind of hard to see at the moment because we're not centered in the same place. But there, that's the same picture we were looking at before, isn't it? Now, why would I want to do this as opposed to the other version? Well, the thing I like about this version is that I can cheat. We picked the point 2, 3, right? I'm just going to go up here. 1, 2, 1, 2, 3. About there. All I did was click in the middle of the damn picture. And it told me the dot I clicked on. Over there in red, you see a box that says T0, Y0. That's the red dot on the curve. It's telling me what the solution looks like without solving it. I don't know what the answer is. But if I start at this point and I go to the right, I should follow the arrows. And if I start at this point and I go to the left, I should follow the arrows backwards. That means my curve is going to follow this slope field all the way around, no matter where I pick. And if you want to put in a particular value, you can go over to one of these and actually change the number. Let's see, I wanted this to be 2, and I wanted this to be 3. Done. And the dot is now exactly on the point 2, 3. You can pick any point you want. When you run it on here, you just touch the dang slope field with your finger, and it draws it.
Where in the slope field with no direction, like they're all kind of circling about something.
They're all kind of looking the same idea, right? Well, let me think about that for a minute. What do the solutions to this equation actually look like? I'm going to turn this off, go back to the paper for a moment. Here's an equation. Tell me, what's derivative of that? E and all that stuff, but that's y again, isn't it? This is the equation that governs my solutions, doesn't it? But I could also multiply by any number I want, couldn't I? I could put y equals k e to the point 0.1 x squared, and then y prime would be 0.2xk e to the point 1 x squared, which is still 0.2xy. So different values of k give me different curves, don't they? And that's what all those different pictures were in here. The different values for k. Positive k's, negative k's, but they're all different values of k. Even if I don't know what the equation is, I still manage to graph it, right? Questions? Is there a place where there's no solution? Is there a place where that function's undefined? What's our domain? What's our interval? Let's go back to last week, Wednesday. We have a function f of xy up here. Where is that function continuous? 0.2 times x times y. Where is that continuous? Everywhere. Polynomial. How about the partial derivative with respect to y? What's the derivative of this function with respect to y? (0.2x), which is continuous everywhere. Means my interval minus infinity to infinity. This is going to work no matter what point you pick. This differential equation has a unique solution for any initial condition, no matter what initial condition you pick. The rectangle goes from minus infinity to infinity, minus infinity to infinity. You put a dot anywhere on the screen, I can draw you a curve through it. And it turns out that that curve looks like this expression, k e to the negative point, e to the 0.1 x squared. Wait a minute. I know e to the x looks like this. So e to the x squared turns all those negative numbers positive, makes them go up faster, and the k would make it faster still. So that's why these kind of look parabola-ish. Their symmetry comes from the symmetry of this expression. More questions? I don't have to know what the solution is going to be. Now, this particular one is a little different, because here, there's no x in the problem. None whatsoever. That doesn't change anything. I can still do exactly the same thing we just did. Let's go back to the grapher. And I'll change our equation here. And instead of having 0.2xy for the y prime, I'll have sine of y. And again, I don't like all the different colors, so I'll turn that off. I'm going to zoom out a little. What do you see going on here? What kind of asymptotes? The horizontal asymptotes. I don't see the oscillation that I think of for sine, do I? When I think of sine of x, I think of it going back and forth, up and down as we go from left to right. We're doing sine of y, and it's telling us about our slope. So when sine is positive, my slopes are up. When sine is negative, my slopes are down. When sine is 0, I have those horizontal asymptotes. But there's no x in here. So no matter what y value you pick, the whole set of arrows going from left to right at that height point the same way. Take a look at the x-axis and look at the arrows just above the x-axis. That's sine of a small positive angle. I'm in the first quadrant, sine is positive. Those arrows go up. But it doesn't matter what x I pick, no matter how far to the left or how far to the right I am, all of these arrows are at the same angle. The slope is always the same. If I get further into the first quadrant, I get more positive angles, right? The sine is going up. But then if I get in the second quadrant, the sine is going down, but it's still positive. So the arrows, as I go from y equals 0 up, the arrows get steeper and then they get less steep as sine goes up and then comes back down. But then when I cross from the third quadrant, sine becomes negative. So all of a sudden my arrows are pointing down and they get more negative, and then they start to become less negative. Now, where are my asymptotes? Where are those horizontal lines? You don't actually see them on here because the arrows didn't line up just right. I'd have to rearrange the frame perfectly to get the arrows to line up just right. Where should I have an asymptote? Okay, but I clearly have more than just that one, right? Where else? But more, not just the even ones. K pi, right? Every multiple pi, sine of pi is 0, sine of 2 pi is 0, sine of minus pi is 0. Those should all be horizontal asymptotes. Pi is an irrational number. This is set up with nice integer values, so my lines don't line up perfectly. But I would expect to see some sort of line. Well, is it really an asymptote? Let's talk about that a little more. By the way, same thing. If I want to do this in slopes, it works exactly the same way. I just have to change up here. Hey, it kept all of those dots we were looking at, didn't it? It didn't even move the dots. But since I moved the arrows, it moved the curves. I can get rid of the dots. You can clear those over here. You can get rid of them at any particular time, or you can just clear the whole thing. Okay. I can take this equation, I can set it equal to a number. That'll give me a curve. But because there are no x's in here, we're going to call this an autonomous differential equation. A lot of the examples we did on Friday were autonomous. The mixing problem with the salt tank, that was autonomous. The population growth, the radioactive decay, those were autonomous problems. The setup of the equation gave me y prime equals stuff in y, but never stuff in x or t on its own. The values where this is equal to 0. Jack, these were the asymptotes you were talking about. So in this case, it's all multiples of pi. But those aren't really asymptotes directly. What does it mean for y prime equals 0? Which makes it a graph of? Say it out loud. Not just any line, a horizontal line. That horizontal line can act as an asymptote, but it's not required to. But if your derivative is 0, is your graph ever going to change? You're stuck there. Those are called critical points because they're where our slope is equal to 0 for our differential equation. But in terms of the graphs themselves, what we have is called an equilibrium solution. And that automatically gives me a solution to my differential equation. If you told me that slope was 0, then nothing I do, no matter what x value I pick, nothing changes. We sometimes call these stationary points. For our differential equation. And these, for an autonomous equation, these are the only solutions that are horizontal lines. If we think of the lineal segments, the little pieces of our direction field, they're all horizontal arrows. So if you're following the horizontal arrows, you never have a chance to go up or down. You just stay going straight across. But what about the sections between the equilibrium solutions? So here, I'm going to make something up. I'm going to give you a different version of the population model. So here's a different equation. The population is proportional to the product of the population itself and a linear function where A and B are constants. Now, since I didn't give you A and B, we could be in deep shit here. But the right-hand side contains no T. It's only P and constants. So that makes this autonomous. It's only going to depend on the p-value as to how my system behaves, not on the t-value. So my left-right motion doesn't matter, only my up-down motion matters. What are the equilibrium solutions for this differential equation? I promise that's not a crazy comment. It's just an algebra question. Yeah. 0. Whatever makes the other part 0. So the equilibrium solutions are where my derivative is 0. So that's either P equals 0 or A minus BP equals 0. P equals A over B. Perfect, wonderful, beautiful. I love it. I'm going to make an assumption for the moment. That when I look at my notes, I really should have written down earlier. I'm going to go back up here and I'm going to say A and B are constants. A and B are both positive. Wait, I don't have to worry about a minus sign floating around on me here. That means that A over B is bigger than 0. Let's draw a number line. Not even an XY graph, just a number line. And I'm going to put two numbers on it, 0 and A over B. And all I know about A over B is it's to the right. So, question. I'm going to make a sign chart like I'm back in Calc 1, only I don't have any numbers, so it's going to mess with me a little. I'm going to have to do this the hard way. Let's pick a number smaller than 0. For P, any number smaller than 0. How about -1? That's easy. What happens if you put in -1 to the slope? dP dt evaluated at P equals -1. All you have to do is put that in here, right? And you get P, well, P is -1. Wait a minute, so I get -1 times A minus B, because the B got multiplied by 1 as well, right? Because P is -1. And A minus B times 1, right? There's a 1 there. Oh, you're right, it's negative. So thank you. Yeah, wait a minute, that's even better. What do you know about the thing in the parentheses? This thing right here. Jalen, I saw your lips moving, so talk a little louder. What'd you say? Well, it's A plus B. It's some constant, but it's not just any constant, it's a positive constant. Each of those numbers is positive. You add two positive things, you get, which means my slope is negative. I'm going to write that right here. A little circle around it. My slope is negative there. Here's the harder one. I need a number between 0 and A over B. I'm going to make my life easy. Let's go exactly halfway. So I'll take A over B, multiply by a half. Let's plug that in up here. dP dt evaluated at P equals A over 2B. So I get A over 2B times A minus B over 2B. Wait a minute. That's not right. With an A up there, right? B times P. Common denominator. So that A becomes 2AB over 2B.
Why would you simplify? Why would you just go straight to common denominator? Like,
Because
why can't AB over 2B, why can't you just eliminate these?
I could.
Okay, you can't.
I could.
That's not cool.
But now my brain says, hey, wait a minute. Okay, if I do, let's do it that way. Those cancel. This is A minus A over 2. A over 2B, right? What do you know about this number? No, let's not do that yet. What do you know about this number inside the parentheses?
It's positive.
And so is the thing on the outside.
Yeah.
Positive. This is positive. I didn't even care what the value was. I just care that it's positive. By the way, when I do this, I get A over 2B times AB over 2B, and lo and behold, the B's cancel there as well. So I'm going to get the same thing. That's a positive. Wait a minute, that means in here, I can put a plus. I got to do it again. I need a number that's bigger than A over B. Sounds good. We'll use 2A over B. We'll put that in. dp dt evaluated p equals 2a over b. 2a over b times a minus b 2a over b. If I cancel the b's, what do I get inside the parenthesis?
A minus two A.
Which is negative now. And this number is positive, so this is a negative item. That's all that matters, is whether the slopes are positive or negative. I now know something about what the picture is going to look like. I have not graphed a single bit of the slope field, have I? But I can already tell you there are two equilibrium lines, two horizontal solutions, and then a section where we're going down, a section where we're going up, and a section where we're going down. Okay, let's take this line and make it the p-axis. So now I'm going to try and picture the slope field. T, P. Here's the origin. Mia, you told me my equilibrium solutions, they were 0 and A over B, right? And A over B was positive. So I have an equilibrium solution here. And I have an equilibrium solution here. And notice there are three pieces of the p-axis. Less than 0, between 0 and A over B, and bigger than A over B. And those are the same three things we just figured out the pluses and minuses for. When we were less than 0, what were our slopes? So I know that all of the arrows on this bottom part of the plane go down. I don't know how much they go down, but I know they go down. I've just drawn one arrow for the whole area. We'll draw a bunch more when we graph it on the computer, but I don't need to do that right now. What's happening between 0 and A over B? They're going up. And bigger than A over B?
Yeah.
They're going down. You get a clean bill of health?
What?
You get a clean bill of health?
Yeah.
Okay, good. What we've just created with this version of the picture, this is called a phase portrait. When we draw it horizontally, we call it a phase line. We will draw a lot more phase portraits. Usually they're in higher dimensions, so they're for not autonomous equations. And we'll do those on the computer. I sure as hell don't want to do them by hand. Well, what we've just created is some information about our differential equation without solving it. Pick an initial condition. Pick a value for a point. If I was back on the slopes app, I could just touch the screen somewhere, right? And it would draw it for me. Let me jump over to slopes. Now we're going to get rid of this equation. I need a value for A, I need a value for B. I need two positive numbers. Somebody give me two numbers. All I need is positive numbers. What'd you say, Jalen? 3 and 8. So 3 minus 8y. There we go. I need to zoom in a little. Oh, we picked a small a. Let me change this, make it 13. Yeah, there we go. Because now my asymptote is at a over b, right? 13 over 8. So that's 13 over 8. It's a little bit bigger than 1. Settings. There we go. Now you can see it a little bit better. But these lines look like they're almost going straight up and down because my t-values are so large. Let's change the t-value. Let's only go from 0 to 4. Done. Now we get a little more of the curviness in there, right? We can see what's going on here. Oh, I forgot something. Let's go back. What did I forget in my equation? The extra y on the outside. On the outside, not the inside. There we go. Now you see exactly what we're talking about. Below, we have arrows that are going down. Between 0 and 13 over 8, we have arrows that are going up. And bigger than 13 over 8, we have arrows that are going down. So if I just picked an initial condition, there's my curve. Pick a different initial condition. What do you notice? Noah, what do you notice that you already told me earlier is going on all of these pictures? But not always, right?
Yeah.
Notice that at the top asymptote, we're coming in towards that one. And on the bottom asymptote, we're going away from it. Because as we go from left to right, the arrows are pointing away from y equals 0. And as we go from left to right, the arrows are pointing in towards 13 over 8. You can see it right here. On both sides vertically, those arrows are pointing in towards that. And down here towards 0, they're pointing away from it. So I have two different kinds of solutions here. I'm going to name them. Because what they're telling me about is the limits as we go to infinity and as we go to minus infinity. As time marches onwards. In this case, as t gets bigger and bigger and bigger, what happens to any solution whose initial condition was negative? We're going to go, wow. If we are looking at the limit as we go to negative infinity, we're getting closer and closer to 0 there, aren't we? If your initial condition is between the two, then we should look something like this. This sort of weird thing with two different asymptotes in two different directions. Where have I seen a function that has two different asymptotes in two different directions before? Hint, trig class. What function does that? Say again? Not tangent. Tangent does this one. This one, it's the inverse tangent. Minus pi over 2 on the left and pi over 2 on the right. Y'all did this before, but it's been a long time. I'm pulling from 3-4 years ago. And then if I'm above a over b, if I'm in that top region, what should happen as t goes off to infinity? As we go from left to right, if I start out up here, It should approach A over B. So that means the closer you get to A over B for a starting point, the more likely you are to go towards it. But when you're close to 0 for a starting point, the more likely you are to go away from it. Remember, we had this version of the graph as well. I'm going to use this idea. So let's suppose we have y equals c. And that's one of our equilibrium solutions. I want to put a sign on either side of c, a plus or a minus. How many options do I have? Plus or minus, right? Put on each side, right? So I got 4 options total. Really, they break down into 3 categories. Either, well, let's start with the easy one. Either they're the same on both sides or the difference on both sides, right? So 2 options to start with. They're the same on both sides. Either it looks like this, or it looks like this. If they're the same on both sides, let's picture what this looks like vertically. If I were to draw the arrows, here's my p-axis. C is on it. If I'm in that top case and we have plus on both sides, then the arrow should be going which way? Up. On both sides. And if we have a minus, we should have arrows going down on both sides. So this is actually not an asymptote the same way on both sides. This is weird. If you're above it, you're going to get close to it. But if you're below it, you're going to go away from it in this bottom case. In this top case, if you're below it, you're going to get close to it. But if you're above it, you're going to get away from it. These are weird. I like the idea of approaching. I'm going to get to a particular number. That sounds like a good idea. Let me look at the other 2 options. My other 2 options are where they're different on either side. Right? Let's draw them vertically again. In the one on the left, what do my arrows look like? Coming up from the bottom, coming down from the top. And over here, down on the bottom, up from the top. Okay, wait a minute. I like these 2 better because I think I can describe what's going on for these 2 better. This one, down from the top, up from the bottom. What's going to happen as we go from left to right? We should close in on that asymptote, right? We should get closer and closer and closer as t goes to infinity. That should look like this. We get closer as we go from left to right. On the other hand, this one over here on the right, I should be blowing away from it on both sides, yes? I should be curving away on both sides. We're going to call this stable versus unstable. So the one where we close in on my asymptote, that's stable. The one where we splay out from my asymptote, that's unstable. We are always talking about going from left to right as t increases, as x increases. So what the hell are those two? They're not stable. They're not unstable. They're kind of halfway. I hope it's no surprise. We're going to call these semi-stable. I did them in the wrong order. I should have started with stable and unstable. My apologies. Questions? For an autonomous differential equation, when that right-hand side equation is only in terms of the y variable, not in terms of t, not in terms of x, then I can guarantee you there will be some equilibrium solution somewhere where y prime is equal to 0. Question is, will it be stable, unstable? And we can tell just by making a sign chart. Ready for another example? What are my equilibrium solutions? Valen? 3 and yeah, 0. I got 2 of them. I think it's easiest to factor this equation in y. I'm just going to make a sign chart, but I can do this in a whole bunch of different ways. Okay. The following can be done in like 6 different ways. Do I put a plus or a minus all the way on the left? Okay, how do I decide whether or not to put a plus or a minus over here to make a sign chart for y prime? My phase line is the signs of y prime. So I just need to know, is y prime positive or negative over here? Plug 1 in. Any value less than 0. Same thing for between 0 and 3. Pick a number between 0 and 3 and plug it in. Pick a number bigger than 3 and plug it in. Except I'm doing it like it's increasing or decreasing, right?
Yeah.
I'm just plugging into y prime. Exactly same sort of sign chart. But you ready for a slightly different version of this sign chart? Say no. I'm not gonna do anything different. Not gonna do anything. There's another way to do this. I'm not gonna actually do anything different. Instead of plugging in numbers, look at this equation. If I asked you to graph this, what's its graph look like? I'm thinking of it as a function of y. It looks like this. A quadratic, right? Not sideways, but it's parabola. And it opens up. Positive, negative, positive. I don't even have to plug stuff in. I know it's a parabola. It's got to go plus, minus, plus, because it opens y, f of y, 0, 3. Plus, minus, plus. Now you absolutely could plug stuff in. That's fine. But now that you have plus, minus, plus, you can also draw those arrows. We're going up here. We're going down here. We're going up here. Which one's stable? Which one's unstable? Which one's semi-stable?
0 stable.
And 3 is?
Uh,
We're going away from 3. We're going in towards 0. Are any of them going in the same direction on both sides? No. So there are no semi-stables. Which means if we were to draw the slope field, we would have 2 horizontal asymptotes. Going from negative to 3 to 5 in x, going from minus 3 to 3 in y, I see it. Hey, look, I drew it just right. There's the horizontal slope field at 0, isn't it? And way up here at 3, there's everything going away from 3. There's my unstable behavior, top, my stable behavior here in the middle. If you start poking around and giving initial conditions, you'll see let me change this so I can see a little bit more up the y-axis. As I go from left to right, I peel away from the line y equals 3. I go towards and converge upon the line y equals 0. Stable equilibrium, I'm going to get closer and closer to this one. Unstable equilibrium, I'm going to blow further and further away from it. Let's go back to our modeling situation. Suppose this was a population. What's this going to tell you? Over time, happens to this population of, I don't know, bacteria, mice, fish.
Stable, but if the temperature rises, I don't know how to.
Well, this doesn't have anything to do with temperature. This just has to do with people or population or things, right? So as time marches on, if I start with a smaller than some critical number, population is going to crash. If I start with bigger than a population, it's going to grow. And in this case, that critical number happens to be 3. I don't know if 3 what units are, but if it's less than 3 whatevers, my population in the long run is going to go to 0. If it's bigger than 3 whatever, my population is going to start growing and grow unrestricted growth. So what kind of model this creates depends on what situation I'm modeling in. Page 45. Here's a picture. Problem 13 here. I have absolutely no idea what the equation is for this differential equation. But this graph is f of y. That's all they told me. This is f of y. So f of y goes plus, minus, plus, minus. And I've got 3 places where it's 0. Negative 2 point, I don't know, 8. Negative 1 and positive 0.8. Just to lay, we can call them A, B, and C if you want, but I figured I'd put some numbers on it. Which means I can make this picture without knowing anything about the equation at all. And it was plus, minus, plus, minus. I don't have anything else. But I know right now which of these equilibriums are stable and which of these are unstable. Look at the way things are going. We're going in, going up where it's positive, we're going down where it's negative. Up where it's positive, down where it's negative. Well, instead of drawing it vertically, I drew it horizontally. So up and down is now right and left. Hey, wait a minute. Is negative 2.8 stable or unstable? I'm going in. Negative 1, 0.8, stable. So now you can picture the slope field. I haven't drawn shit, but I can tell you right now if I have those asymptotes, I know what's going on. If you started with a population of 5 at time 0, what would happen in the long run? It would collapse down to 0.8. If you started with a population between, I don't know how this works, negative 1 and 0.8, it would grow towards 0.8. So I have stable behavior here. In the long run, we get close to this number, or we get close to this number. What we don't get as we go from left to right is close to negative 1. We keep going away from it. Now, before you freak out about this idea of stable and unstable, I have a challenge for you. Find a coin. You don't have to do it right now. Find a coin. There are 3 different ways you can lay this coin unmoving on a table. Heads up, tails up, or if you're really good at it, you can balance that sucker on edge. Which of those 2 equilibria are stable? That one? You disturb it even a little bit and it collapses, right? You disturb it even a little bit and you end up at one of the other 2. On edge, heads, tails. These make sense as physical ideas. If you have a cone, you can balance it 2 ways, with the circle part down or on its point. Circle part down is stable. On the point isn't very stable, is it? Stable versus unstable has a physical reality of a meaning in this case. Questions? Please notice, back in our picture, of all of these graphs with the slopes, we had a whole bunch of graphs down here below 0, a whole bunch of graphs up there above 3, a whole bunch of graphs in the middle between 0 and 3. And they all look just about the same, don't they? Because our differential equation had no t values in it. This is y squared minus 3y. There's no t values over there at all. So no matter where you choose to start, from left to right, the graph looks the same. When you are close to the line y equals 3, but slightly below it, your graph has a very small negative slope, just a little negative. But as you go down, that negative gets bigger. As you keep going down, it gets a little less negative until you're really close to 0 and it starts to flatten out completely. Every one of those graphs in the middle there is the same, except for how far left or right it is. Every graph on the bottom here is the same, except for how far left or right it is. This is called translation invariance. These graphs are invariant, they don't change, no matter how far left or right we are. And that's because the differential equation is autonomous. It doesn't change in terms of the x value at all. So I just did a whole lot of solving things without ever actually solving a differential equation. I haven't come up with a single equation in this picture at all. I don't know what any of the curves look like. I'm not even sure how to get them here yet. I would love to be able to solve this and tell you what these funky colored curves are. I don't know yet. But I still managed to get a lot of information without actually solving. This is the qualitative type of information I can get without ever actually solving the equation. So what's next? I should probably try and solve some of these things. Probably. That would be a good idea. But is that what we're actually doing next? This is where I need my schedule again, which I left back of this. Because of Labor Day, what are we actually doing tomorrow? We're not actually solving these until Friday. So Wednesday, tomorrow, Chapter 1, Section 3 on models, Chapter 2, Section 1 on solving without solving. So bring me your questions tomorrow. I'll see you over in Boyle. Write it down. What time is it? It's a 5-minute largesse from me to you. I'll call it back at some time. I'll see you tomorrow.